Welcome back. This is Chapter 2, Section 1, and we're looking at isotopes and how isotopes of different elements can be used as research tools because we can use those changes that occur over time in certain elements to determine how old something is. So it's used for dating of fossils, for example. If this is unclear to you, ask me in class. But I think many of you probably have already talked about this in the past. So let's go to the periodic table, which you know already and love just as I do, because it's a brilliant display and organization of all the known chemical elements. And also most of these are naturally occurring, but there are some that are man-made. But we're interested in biology and the ones that are typically appear in these rows or periods at the very top of the table. So we'll be looking at some in much more detail than others. But the table basically shows us that the rows, which are called periods, show us that the next one over, if we're reading from left to right, has an atomic number that is a 1 greater. So this lithium here is 3, beryllium is 4, and then we go to boron is 5, and so that tells us the number of protons in an atom of each of these types of elements. And so that's from left to right. And then up from going from top to bottom, down the group, or sometimes called a family, chemical family, this tells us a lot about that these all have some properties that are in common, and that we'll get into how these ones here in particular will react to others on the table. So first of all, we know that an atom itself is neutral. So if you just look at an atom, pluck an atom off of one of the periodic table, any atom, and you're going to find that it has no net charge because it has the same number of protons as it does electrons. And the number of electrons are actually the number of protons equals the number of electrons, but it's really the number of protons. So notice there's an error here that we use to represent the atomic number. This is a Bohr model. Looks like a bullseye target, and it's useful in that it kind of gives us an idea of where electrons could be found relative to the nucleus, how far away, and how many would be in these different areas that are energy levels, sometimes called energy shells. There is a rule that only 2 electrons can be close to a nucleus, and then after that you can get up to 8 electrons usually out here, and then another 8 or sometimes 18 electrons depending on where we are on the table. So there's some nice patterns that we can follow when we're looking at the periodic table. And this is a good depiction of that. So the outer energy level on any of these atoms, the ones that are in red, are called valence shells. And if that valence shell is filled to its maximum capacity, such as helium, such as neon, notice that we're in the second energy level here and it has 8. And all the ones in this column actually have their energy levels filled up to the maximum. These are all very stable elements. These would be the noble gases. Whereas the ones on this side, which would be on the left-hand side of the table, are unstable because they only have a lonely electron in that outer energy level, and therefore could fit a lot more of these. That makes it somewhat of an unstable position. So we're going to look at these in particular with some chemicals and some compounds, some ionic compounds coming up. I think this basically is looking at a lot of the same, although it does bring up this idea that if you have 8 electrons and that's the capacity of the outer energy level, that's called the octet rule. So first you have the first 2 electrons only can fit close to the nucleus. It's called a duet, like when you sing a duet. And then when you have 8 electrons, that's an octet. So Bohr models are really helpful, but really electrons don't travel in those circles like at an amusement park. Really, they travel much more like this, and they travel in these things we look at as orbitals. So they have very particular shapes depending on where we are relative to the nucleus. You can see here this red ring here is showing that that first energy level has a spherical shape like a sphere, and that's really its only option because there's only one. But when you get into the energy levels or orbitals, or energy levels farther from the nucleus, the electrons go in somewhat different positions. So we'll talk a little bit about this, and it does have relevance to certain formations of chemical compounds. But if you haven't had any of this, don't worry, don't stress over it. We'll apply it when it's necessary. And you can see this on this link that you have in your book. So go to that link. Electrons, though, are the things which are important because they tell us how an atom will react with other atoms. So the protons are the identity, but the electrons tell us what they do, what an atom of any element will do. And that depends on how those electrons are in those outer energy levels. So we'll look at chemical reactions, and when we talk about reactions, we're really looking at things which are, in this case, we're looking at the reactants on the left, and we're looking at products on the right, and an arrow that tells us the direction of that reaction. So in this case, the reactants, if you can read this, you would read that this is 2 molecules of this compound called H2O2, which is hydrogen peroxide. And hydrogen peroxide, 2 molecules of hydrogen peroxide will break down or form these products to water molecules and 1 molecule of oxygen. But this little 2 tells us that oxygen is a diatomic, means it has 2 atoms in it, molecule. It's not a compound, it's a molecule. And the 2, these coefficients that are in front of the formula, are letting us know that there's 2 of this. There's 2 of this. There's only 1 of this, so 2, but it has 2 atoms that make it up. But more importantly is looking at what's happening with these arrows. So certain chemical reactions are irreversible. This means it's going to go this way and only this way until all the products are made and all the reactants are used up. In biochemistry and in the body, very often we see these types of reactions, reversible reactions, and they are going to be, notice the arrow goes both ways, so these reactants can form this product, and this product can turn around and then decompose back into these reactants. So we're going to see this kind of happening in different biochemical pathways depending on the situation. We'll look at this, especially with regards to looking at some of the metabolic pathways. So stay tuned on that. A chemical bond is really what's holding these molecules together, and it's this force that holds them together, and it has to do, again, with electrons. So when we have these 3 atoms, 2 hydrogen and 1 oxygen, we're only looking at their outer energy levels, these valence electrons. Hydrogen only has 1, so there it is. Oxygen has 2 other electrons that would be placed in here if we're going to draw this as a Bohr model. But what we're really just caring about, and when we talk about bonds, is what's on the very last energy level. And with oxygen, you can see that there's 2 electrons here. So these are paired. These are paired. And these electrons aren't paired, so these are unshared or unpaired electrons. But the fact is that they can share with something else, in this case hydrogen. So if you look at the reaction, these are the reactants, 2 hydrogen, 1 oxygen, are going to yield this, which you are familiar with, which is water. And the way water forms is through this bonding, this sharing of electrons of hydrogen with oxygen. So it shares this unpaired electron. Now we have this bond. Here it is again. And that's forming a covalent bond that holds this molecule together. So this is water, H2O. And you might notice here that it's a bent molecule. So that has some relevance. So we'll talk about why this is actually hugely important in biology. Sometimes an atom will share an unshared pair of electron with itself. In this case, we have oxygen and an oxygen. And now you can see what happens is that those unshared electrons are able to pair up with in actually forming a double bond. So this is a covalent bond. It's a double bond, 2 places where you see the sharing going on. This is O2. This is the way we typically find oxygen. It's a stable molecule like this. We can call it a molecule because it's a covalent bond. It's a molecule. It's a covalent bond. And it's a double bond. And if you notice that, well, probably you couldn't tell too well, but this double bond is actually stronger than a single bond. So this really is a pretty strong bond. All right. Now, the other scenario is that some atoms don't necessarily all share electrons. So there are other types of bonds that can form. This one is an ionic, shows ionic bonding formed between a metal, sodium, and a nonmetal, chlorine. And when they join together, they both become attracted to each other because they have opposite charges. So how that happens is that sodium, here's its outer energy level, its valence electron sitting right there. Valence means it's the one that's available here on the outer level to do something. This is an unstable condition for sodium. Sodium will then give away its electron, which is attracted to chlorine. Chlorine just needs one more electron, so it's kind of greedy. If it can get that one electron, then it becomes stable. When it does, it becomes an ion of chloride, and it joins with sodium, which is also an ion, forming the ionic compound, sodium chloride. So polar bonds are ones that have an unequal sharing of the electrons, and nonpolar are those which don't. And so we have some examples here of some polar covalent bonds, and water being a great example of that, because oxygen in a water molecule has a stronger pull on electrons, and so the electrons tend to hang out closer to the oxygen than they do the hydrogen. So that's the polar covalent. There are nonpolar covalent bonds too, and those are ones in which it's still a covalent bond sharing of electrons. However, it's a pretty equal sharing. There isn't any real pull in any direction, either because of the geometry of the molecule, or just because there's they basically have the same ability to pull on electrons as each other. So these are non-polar. Methane's a good example of that. We're going to skip over this picture because we need to, in the last minute or so, talk a little bit about these 2 weaker bonds called hydrogen bonds and van der Waals interactions. These are weaker bonds, don't require energy to break. However, they have some great significance in biology, and we're going to see that in very particular scenarios coming up. So there you go.